Okay, we're now going to talk about one of the most interesting series. This is called the geometric series. And the geometric series will play a huge role in all of our works to follow because it actually has an x. So it has an x. So it is this following function of x. It is x to the power of n, and we're going to sum this from 0 to infinity. If you don't like 0, this is also equivalent to the sum from 1 to infinity of x to the power of n minus 1. This is true. This is clear if we just check the first few terms. They're both correct. You can use whichever one is more convenient. I like the 0 personally because it's less writing. So the geometric series is very unique because f of x has a closed form. Rather, you can call it explicit form. And so the claim is actually that f of x is this very simple looking function 1 over 1 minus x, which has this behavior. It blows up when x equals 1. So the reason is telescoping. But it's not quite, it's not in itself a telescoping series, but I'm going to use a telescoping method to prove this. So let's start with f of x, and I'm just going to write out the terms. F plus x, 1 plus x squared plus x cubed, and so on. Now, what's really funny here is if I actually multiply f of x times x, I get the following. I get x plus x squared plus x cubed. If I associate, of course, x with 1, then you see why this has to be true. So notice that all the terms are the same, except 1. So I'm going to subtract. I will see that then the f of x minus f times x is 1. Everything cancels. All the terms cancel except for 1. So now I'm going to solve for f after I factor. And so I conclude that f of x is equal to 1 over 1 minus x. This is a really awesome trick, and I wish it could apply to more series, but it just does not apply to more series. It's just a once in a mathematical function lifetime kind of trick. So I just want to also say it's only valid if absolute value of x is less than 1. So for example, 1/2 to the nth power. This is okay. And the claim then is that 1 plus 1/2 plus 1/4 plus 1/8. This is actually equal to 1 over 1 minus 1/2, or in other words, is 2. So this is kind of reasonable, right? Because 1 plus 0.5 plus 0.25 plus 0.125 plus 0.0625. Well, I think this is 1.5. This is 0.375. And if I add it to this one, then I should get something like, let's see if I do this math correctly, 0.4375. So now I'm going to add these two very quickly, and I get 1.9375. So it's rather close to 2. And the more terms you take, the closer it gets to 2. I can add more and more terms, and it'll just get better and better. It will never be exactly 2. but you can make it arbitrarily close if n gets bigger. And I think it's also worth talking about just the case x equals 0.1. The series 0.1 to the nth power is also known as 1 plus 0.1 plus 0.01 plus 0.001 plus 0.0001 plus everything in between. So we end up with 1.111111111. This is actually equal to 1.1 bar. So the amazing thing then is if I use now the geometric series 1 over 1 minus x with x equals 0.1, I get 1 over 0.9. So this is also known as 10 ninths. So therefore, 1.1 bar is actually just 10 ninths. So we have taken a continued decimal expansion, an infinite decimal expansion. We've actually written it as a closed form fraction. I think this trick is kind of fun. So how about we just try one more of these? Let's try 0.123 bar. So that means 0.123, 123, 123, 123, and so on. So here's the trick. This is going to be equal to 123 over 1,000 plus 123 over 1,000 squared plus 123 over 1,000 cubed, and so on. So it's actually not a geometric series in powers of 123. It's actually a geometric series in 1,000s. And there's an extra 123 on the outside. So I'm just going to factor that out. So I get 1 plus 1 over 1,000 plus 1 over 1,000 squared, and so on. So now I'm going to use the geometric series, and I get 123 divided by 1,000 times 1 over 1 minus 1 over 1,000. So this should be 999 over 1,000. So I should get overall 1,000 divided by 999. And let's just notice that these thousands cancel. So I should just get 123 divided by 999. So that's pretty surprising. I actually didn't see this when I was in high school or anything. So I thought this was a pretty neat trick about decimal expansions. In general, like if I did 1, 2, 3, 4, you can guess it would probably be 1, 2, 3, 4 divided by 999, just by comparing it with our previous one, which we got 10 over 9. Okay, so that's kind of a neat application of geometric series when x is small, but actually if x is large, it's a divergent series, and so it's not valid. At least it's not valid in this course. If you ask any physicist, they will tell you it has some sum, and they would be right in some sense, but they're also wrong. So let's not go there. So the reason it diverges, let's just consider a couple of cases. So if I just take x equals 1, it's this series. It's that area, so that should be infinity. If I take the series -1 to the nth power, this should just be 1 minus 1 plus 1 minus 1 plus 1 minus 1. So it's an oscillating series, and it never settles down to a number. In other words, the limit of -1 to the nth power, it does not exist. This is a big problem for series. So in this case, it also diverges. So the sum, partial sums of -1 to the n, they're either 1 or 0. They never converge to anything. So and then for x bigger than 1, it's you're adding a small. So you're adding something like a small plus a, how about I do this? So it's like A plus A plus A plus A. It's not, you kind of get the idea, right? So you're adding bigger and bigger things each time. Your series is not going to converge. It's just going to blow up on you. Because really, we're taking this area now, and we're adding bigger and bigger chunks at each stage. This just blows up. Okay. So the last thing I want to mention is that you can also get the partial sums of geometric series using the same way. So and this is actually how I proved the convergence. You can just use the partial sums and take a limit. So let me just write this 0 to n of x to the n. That's called, I'll call this Sn, the sum from 0 to n. And so now I'm going to just write those terms out. 1 plus x plus all the way to x to the n. So as before, I'm going to multiply by s. So I get x plus everything. But now I'm going to have an extra term. And before, this was absorbed into the infinity dot dot dots. So now if I subtract, I get Sn minus x times Sn equals everything dies except for first and the last. It's like telescoping. So therefore, Sn is, if I factor that x minus 1 out, it should look like this. So therefore, if absolute value of x is less than 1, then xn goes to 0. On the other hand, if it's equal to 1, or if it's well, if it's equal to 1, you see that there's a problem here, right? Because there's a singularity. You're dividing by 0. So that's obviously there's kind of an issue there. But if it's greater than 1, then you can see clearly that this term here will actually blow up on you as it goes to infinity. So this is another way to understand the geometric series in terms of partial sums. Okay, I think this is all I have for today. Thanks for watching.